So what I'm going to do for the homework for chapter 4 is I'm going to kind of try and bunch it in all in one thing because it's kind of the same idea. So what I'm going to talk about real quick is how you graph rational functions with a couple of extra exercises. And to start with, I'm going to look at checkpoint exercise 13. And this is from 4.1. So what I want to start with and talk about is first, I don't know why that screen popped up. What I first want to talk about is specifically what happens with an x-intercept. So the x-intercept is where it hits the x-axis, so we know where y is equal to 0. And particularly that's where the numerator has to be equal to 0, because the denominator can't be 0 because you can't divide by 0. So we're looking for where x cubed is equal to 0. And that's only going to happen at 0. So it only has one x-intercept. Now if we try to find the y-intercept, if we try and find the y-intercept of this graph, that's going to be where x is equal to 0. So if I plug 0 in everywhere, well, I'm going to get the exact same thing back because this is a function. I plug 0 in, I got to get 0 back. So I know this point right here is going to be on the graph. So I know I have one intercept, and that's at the origin. So now I got to talk about the asymptotes of this. So if we're going to talk about the asymptotes, we first got to talk about our vertical ones. The vertical ones are where the denominator is equal to 0. And if you look at this, where this is equal to 0, we can factor that because it's equal to x plus 1 times x minus 1. So I have two different spots where it's going to be a vertical asymptote, at positive 1 and negative 1. And this is kind of how the two look. This should be dotted lines, but every time I draw dotted lines with this program, they seem to disappear. So those are my two vertical asymptotes. So they are at x equals negative 1, x equals positive 1. In terms of horizontal, if you notice, we have a degree 3 over a degree 2. So the degree in the numerator is bigger. So we have a degree that's bigger in the numerator. So that means there's no horizontal asymptotes. It doesn't follow any. Now comes the hard part, because if you look at this, this is going to require you looking at stuff from 4.2. The degree in the numerator is exactly one more than the degree in the denominator. So that indicates the presence of a slant asymptote. So we have to take and divide this by the denominator. And we are going to get what the slant asymptote is. So I divide x squared into x cubed, and I get x. Oops. That didn't work. So I'm going to subtract all of that. What I'm left with is a positive x squared, or 1x. And I have nothing else, so that's over my remainder, or over what I'm divided by. So this here, what is left is what my slant asymptote is. So this right here is my slant asymptote. So my graph tends to follow this as it gets bigger. That was a Very terrible drawing of that line, but I'll try it again. So, there we go. So, we have 3 parts here. So my suggestion to you is to start plugging in points between this asymptote and negative infinity. So in between here to get a pattern, because my guess is it's going to come from this way and it's going to go up like this. And then plug a few points in here to see what happens. And then plug in a few points over here and see what happens, because I'm guessing actually, my guess is actually it'll look like something like this. It'll graph like this, and then something will kind of wave around, and then it'll go back up like that. But you can't really know unless you plot points. Okay? So, we'll take a look at this one here, and I'll just show you just a couple things the same way. So first of all, very quickly looking at this, to find the x-intercept, so where the numerator is equal to 0, that's going to be at 4. The y-intercept is where x is equal to 0. So if I plug in 0, I'm going to get negative 4 over negative 16, so that's 1/4. So I have 2 points on here. I'm looking for asymptotes. Now here's where it's interesting, because if I do something like this, and I look at this and I say, well, the denominator can be factored into this. So I have 2 different asymptotes at 4. Oops. At a positive 4 and a negative 4. But we already have an x value that we can have for intercept. So what happens here? Well, what really happens is the problem that this expression can be simplified. So what this really looks like is this. So we can simplify this by just saying, alright, it's 1 over x plus 4. So all of this really just doesn't even help us anymore, because I simplified this by canceling out a factor. It's just a repeated factor. So really this is my actual function that I'm trying to simplify. So I got to go through the same results. I got to ask myself, where is the graph have an x-intercept? Well, where is the numerator equal to 0? Well, it's not equal to 0. You can't have 1 equal to 0, so there's no x-intercept. There is none. The y-intercept, so I let x equal 0, I still get 0 comma 1/4. So that's still the same. Now I have to plug in and find out where my asymptote is. And if you look, the degree of the numerator is 1 less than the degree of the denominator. So we are going to have a horizontal asymptote at the x-axis. Okay, so that's the first asymptote. This vertical asymptote is where the denominator is equal to 0. Okay, and the denominator is equal to 0 at negative 4. So I'm just going to say, well, where is that equal to 0? It's equal to 0 at negative 4. So I'm going to just put a dotted line at -4, like this. Notice how they're just disappearing on me. So it's got to follow this, go through the x-axis or y-axis at 1/4, and then it's just going to follow the x-axis like that. And then this way, it's going to go the other way. Like that. So there is your graph. And again, what I would suggest you do, if you don't have a graphing calculator, is just pick a few points and plot them on either side of the asymptote, or multiple asymptotes if you have them. For instance, if we have one, I'd pick a couple on this side, a couple on this side, and then get a picture for what it looks like. Beyond that, I think